The fancy definition of the moment of inertia is: the moment of inertia of a rigid body determines the torque needed for a desired angular acceleration about a rotational axis. It depends on the body's mass distribution and the axis chosen, with larger moments requiring more torque to change the body's rotation. Now, for everyone who doesn't exactly care about the dictionary definition and wants to know what this actually means to them, we did this in class with the hula hoop and the angle that Miss Durso made. Using our guesstimation skills, we would guess which object would go down the ramp faster due to its size. And as anyone would guess, the bigger object would take longer to roll down that slope than the smaller objects would. Now, as simple as this entire concept seems, it actually has a lot more to do with our daily lives than anyone would ever think. This is our attempt to show you how we can measure the moment of inertia and even how sometimes it can be used in our daily lives. Enjoy. The circumference of the large tire was 333 centimeters, and its radius was 53 centimeters. Our hypothesis was that the tire would roll down the hill the slowest due to its size compared to the other objects. Our initial thoughts were that it would roll down the hill 3 times. As you can see in all 3 of our tests, the tire spun down the hill 2.5 times instead of our projected 3. The circumference of the small tire was 220 centimeters and its radius was 35 centimeters. Our hypothesis was that we originally thought that the small tire would rotate more than the large tire, but then less than the basketball. We suspected a total of 5 rotations. Our tests with the small tire proved that the tire would roll 4.5 times down the hill instead of our projected 5. The basketball had a circumference of 79 centimeters and a radius of 12.5 centimeters. Our hypothesis was that we originally thought that the basketball would rotate more than all of the other objects that we had. We suspected a total of 10 rotations from the basketball. In our tests with the basketball, we had 3 different results. The first showed 10 rotations, the second showed 11 rotations, and the third showed 10.5. Our hypothesis of 10 rotations was close to the actual result that we found to be true. Now, what anybody should take away from this entire experiment is that if you have 3 objects, one being the largest, 2 being the medium, and the third being the smallest, the largest object will always roll down the slope the slowest, and the smallest object will always roll down the slope the fastest. The reason behind this is all due to the moment of inertia. The larger object needs more torque to be moved down the hill. And when these objects have to create the torque themselves, it takes longer for the larger object to create torque rather than the smaller object to create the torque. And once you understand all of this, then you get what the moment of inertia is. Now let's apply this sucker to some math. For our math problem, we actually went back to the lab that we did on this in class, and we used number 7 out of our lab book. So here's the question. There were 4 parts to this question, A being the force on the platter, B being the torque on the platter, C the average angular speed, and D the angular momentum of the platter. In our math problem, we just replaced our numbers from our experiment with those of the lab. Now here it is. To find the force on the tire, you simply have to multiply 10, which is gravity, by its weight, which is 40.8 kilograms, to get 408 newtons. To find the amount of torque that was on the big tire, you multiply the radius, which is 0.53 meters, by the amount of newtons, which was 408, to get 216.24 newton meters of torque. Finding the angular speed of the tire requires a few more steps. First, you must obtain the radians per second, which in our case, you take 2.5 rotations in 9 seconds of time and divide those. When you divide them, you get 0.277 rotations per second. Then you take that number and divide it by 2 to get your angular speed of your tire, which in our case, again, was 0.13. Then, to find the angular momentum, you take the radius, the angular speed, and the original weight of the tire, and you multiply them all together. We got 3.003 as our angular momentum. To find the answers to all of these questions for our other 2 subjects, you would do the exact same thing as we just did in those problems there. The only difference this time that you would have is that you would have to use different measurements for the different objects you used in your experiment. And really, that's it for the moment of inertia. And even after our long explanation of moment of inertia, if you don't think that it has much to do with our daily lives, just think about all those cats that Mrs. Durso slings around in her physics problems, because those have to do with the moment of inertia.